Video we're going to start section 3.4, the chain rule. And this is a pretty big section. We'll spend a number of days on it in class. Real important to keep up with the homework. In this section we are going to find the derivative of composite functions using the chain rule. And what's a composite function? Remember, it's a function within a function. Like sine of x is a function, but the sine of x to the third is a composite. You know, this would sort of be our outer function, the sine function, and the inner function would be this something to the third power. We're going to find the derivative of a function with the general power rule. You know, we're going to use the chain rule to expand the power rule that we currently have to the general power rule. We'll simplify the derivative of a function just using algebra. Find the derivative of our transcendental functions using the chain rule. And find the derivative of a function involving the natural log function. And then we'll also define and differentiate exponential functions that have bases other than e, because we've talked about base e previously. Okay, example one. This concept, what the chain rule is, as we go through this example and we discuss this, you know, it might be a little confusing. Once we get into the problems and you see how it's actually applied, you'll see it's not that bad at all. But I would recommend coming back, you know, after you do some of the homework and reviewing this example, and especially reading what we have here in the notes, and even crack open that book and read exactly what's in the book too. It'll greatly help your understanding. So finding the derivative of a composite function. A set of gears is constructed as shown in the figure, such that the second and third gears are on the same axle. As the first axle revolves, it drives the second axle, which in turn drives the third. Let y, u, and x represent the numbers of revolution per minute of these axles, the first, second, and third respectively. So they want us to find dy du, the derivative of y with respect to the u, derivative of u dx, derivative of u with respect to x, and dy dx, the derivative of y with respect to x. Remember, each of these is a derivative, and a derivative is just a rate of change. We're rotating these handles going around, and the gears drive other gears on different axles. And finally, we want to show that dy dx, the change in y with respect to the x-axis, is equal to dy du times du dx. Now, the way this notation was chosen, we'll get into later in the course, and it was picked to make things simpler later on. And if you look at this, it's almost like, if we look at the right-hand side, dy du times du dx, on this diagonal, we do notice that du is on that same numerator and denominator on each side. So we could cancel those out, you know, reduce that down to a 1, and if we multiplied straight across now, we would have dy dx. And we just want to show that. And again, you know, we're talking about rates of change. So here's our handle. You know, we put our hand on here and we start spinning this axle around. You know, the rate that we spin that affects this gear. You know, as we spin the handle, this gear will rotate at the exact same amount. This small gear is tied into the bigger gear. So as the small gear goes, it's going to change, or it's going to rotate gear number 2. And as gear number 2 rotates, it's on the same axle, the U axle, with gear 3. And then, you know, as this big wheel turns, the smaller wheel turns, and this smaller gear 3 is also meshed into a gear 4 on a different axle. So we spin this. If we spin this slow, it makes this wheel go slow, and then in turn slows this down, which is going to slow down gear 4. But they're not all slowing down at the same rate. You know, it all depends on what we're cranking this handle with, how many revolutions per minute. So here in Theorem 2.10, we have our chain rule. If y equals f of u is a differentiable function, and u is equal to some other function, g of x. So we could replace this u with g of x and have f of g of x. F of g of x. And you should remember that from pre-calc. So if y equals f of u is a differentiable function, and u is this other inner function g of x, is a differentiable function of x, then y equals f of g of x, the composite function, is a differentiable function of x. And dy dx is equal to these two pieces multiplied, dy du times du dx. Or in equivalent form, we could write the derivative with respect to x of this composite function, f of g of x, is f prime of g of x times g's derivative, g prime. And again, this is going to be kind of confusing the first time you see it. As we work through the first few examples and you're working on some homework tonight, come back and reread over this. It'll make a lot more sense. So when applying the chain rule, it's helpful to think of the composite function f compose g as having two parts, the inner part and the outer part. Here is our outer function, f of something. And when we replace our inner function with a u, we're going to have f of something. That is our outer function. The inner function is g of x. Or up in the theorem box here, we said u was the same as g of x. So we could replace that g of x with a u. F of g of x is the same as f of u when we let u equal g of x, that inner function. The derivative of y equals f of u is the derivative of the outer function at the inner function u times the derivative of the inner function. So we have y equals f of u. Well, that's just f prime of u times the inner function's derivative, u prime. Again, a little confusing when we do a couple examples. This will make a lot more sense. In example 2, we're not actually deriving these. They just want us to decompose the composite function, sort of training your brain to figure out which is your inner function. Remember, the notation we've been using is f of g of x. We're trying in this exercise, example 2, just to identify what the inner function is here. And I think the first one, letter A, is one of the harder ones. Because, a clue to an inner function could be parentheses raised to a power, as we'll see down there in letter C. So when I look at letter A, this is our composite function, f of g of x. They're asking us, what does u equal? What is our inner function? Well, I'm looking at that denominator, and if I put a set of parentheses around there, and I would give it the exponent of the first power. So I could say, well, my inner function, my g of x, is going to be whatever's in the parentheses. U equals this quantity, x plus 1. And then if I wanted to rewrite the original equation in terms of u, I could now write y equals 1 over u, or u to the negative 1 power would also work. Letter B, y equals sine of 2x. Whenever you're dealing with a trig function. A lot of times when I was in high school, I remember teachers always had parentheses around whatever you were taking the sine of. And that lets me focus in on that 2x. If that was just sine of x, the inner function would just be the x. But now it's 2x. So here we're going to let u equal 2x. And then when we rewrite our original function in terms of u, we could write sine equal, or y equals, the sine of u. In letter A, I did say that, a parentheses can be a dead giveaway as to what that inner function might be. Remember, there are parentheses involved here if you want to think about it this way. We could rewrite this as 3x squared minus x plus 1 to the 1/2 power. Or you could just think, sort of like parentheses are a grouping symbol, so is the radical sign. So a good idea might be whatever is under that radical. We might want to let u equal what's under the radical, 3x squared minus x plus 1. And if we let u equal what's under the radical, we rewrite the original function as y equals the square root of u, or u to the 1/2. In letter D, remember tan squared of x. When you see the squared is right on top of the trig function, you can sort of put parentheses around it and move that squared out. So if you wanted to rewrite this, you could rewrite it as the tan of x quantity squared. And again, where parentheses are a good giveaway to the inner function, here we do have an inner function. We have something raised to a power. So we're going to let that something be our inner function, the tan of x. Then we can rewrite the original function as, instead of tan x squared, or tan squared x, it'd just be y equals u squared. So again, there's some homework problems that they're just asking you to decompose this composite function. Don't go all the way and find the actual derivative, or you're doing a little too much work. Okay, now finally, use the chain rule. Example 3. There we go. So we have, I'm just going to rewrite the equation, y equals quantity, x squared plus 1 to the 3rd. So for the chain rule, we want to take this derivative, y prime. The inner function is this. So I'm not going to rewrite everything in terms of u. I'm just going to say, well, just like the power rule, we're going to bring this exponent down front. So we're going to have a 3 times this quantity, whatever that quantity is, x squared plus 1 in this case, to 1 power lower. Drop that third power down to a squared. And now the chain rule comes into effect, and we're going to multiply this by the inner function's derivative. What is the derivative of this inner function? Well, the derivative of x squared is 2x. That 1 just derives away. So we're going to multiply this times 2x. And we can collect up some like terms, or just do a little multiplication here. This 3 times 2x would be a 6x. And then we'll have our parentheses quantity squared. You know, I wouldn't recommend foiling that out. That's make it a little more complicated. So there is our derivative with the chain rule. And that leads us to the general power rule. When we take the power rule and add the chain rule into it, the function in example 3 is an example of one of the most common types of composites. Y equals something, u of x to the nth power. The rule for differentiating such functions is called the general power rule. And it is a special case of the chain rule. So our function is ux to the nth power. U is a differentiable function of x, and n is a rational number. So then our derivative, dy dx, is, we bring that exponent down front, whatever that n was, times the inner function to 1 power lower, times the derivative of the inner function with respect to x, du dx. Or equivalently, this is a lot easier to see. We're taking the derivative of u to the nth power. Well, that derivative is n times u to the n minus 1 power times u prime. You know, that chain rule creates that little extra piece at the end that we multiply by. So apply the general power rule. We want to find the derivative of this quantity to the third power. Again, I'm just going to rewrite it. F of x is, we have our 3x minus 2x squared all to the third power. We want that derivative, f prime of x. So what is the inner function? Here's our inner function. This is something raised to a power. So if you want to think about this as a u, our inner function, that would be u to the third power. So we want to take that derivative. Bring the 3 down front. Exponent drops down front. 3 times that same quantity. 3x minus 2x squared to 1 power lower. So we've taken the derivative of f of u. Now we want to do the u prime. So our inner function, again, I underlined in red here. We want to multiply by that derivative. Derivative of 3x is 3, minus 2x squared's derivative is 4x. Let's see, I believe the example in the book leaves it exactly like that. If you wanted to distribute the 3 across, this set of parentheses, I guess that'd be all right, but, it'd just be something you could factor out later. Okay, let's try a couple harder examples here. I guess example 5 isn't too bad. Differentiating a function with a radical. Find all points on the graph of, here's our function, f of x is the third root of the quantity x squared minus 1 quantity squared, for which the derivative f prime of x is equal to 0, and for those which the derivative f prime of x does not exist. Remember, the derivative f prime of x equal to 0, what does that mean? Well, that would be where it would have a horizontal tangent line. That would be a point on the graph where you'd have something like this, and the point of tangency would have a horizontal tangent line. The slope of that would be 0. So we need to take our function f of x, and I'm going to rewrite it not as a radical, but with a rational exponent. So I'm going to have my x squared minus 1 quantity squared. Oops. Well, that's what's under my radical x squared minus 1, and it needs its rational exponent, and we make that from the exponent under the radical and the index. So here our exponent would be 2/3. So there's our function f of x. Of course, we want to take the derivative, f prime of x, and that will be no problem but the chain rule. Bring the 2/3 down front. 2/3 times our quantity, x squared minus 1, to 1 power lower. So what do we do? Subtract 2/3 minus 1 gives us negative 1/3 is our new exponent. And then don't forget to tack on by the chain rule. The derivative of the inner function is just a nice simple 2x. Let's see here. I guess we can clean some stuff up and move this quantity to the negative exponent down to the denominator. First, let's get rid of that 2/3 and multiply it by the 2x. 2/3 times 2x is going to be 4x over 3. And then this piece of our function, since it's all multiplied together, it's got that negative exponent. We want to drop that down to the denominator, x squared minus 1, and down here it is to the positive 1/3 power. Now, back to the problem here, we found the derivative f prime of x, and they want us to find all points where the derivative is equal to 0, and those for which the derivative does not exist. So when do those happen? We have a fraction, a quotient. When will this whole thing be equal to 0? F prime of x equals 0 when what? When the numerator equals 0. When 4x equals 0. And when does 4x equal 0? Well, the only time that equals 0 is when x is 0. So the derivative, f prime of x, is 0, or it has a horizontal tangent line only at one point, right above or below the x-axis, wherever it occurs on the graph. Next, they're asking us to find where it does not exist. F prime of x dne, what do we need to do to this derivative to get it to not exist? Well, since it's a fraction, we don't want to divide by 0. The derivative does not exist when the denominator is equal to 0. So we sort of have to solve this for x. We can divide both sides by 3, and that 3 will drop off. Let's see, we can raise each side to the third power. This to the third power will wipe out the 1/3 exponent, so we're just left with x squared minus 1. We'd also raise 0 to the third power, and that is 0. Now we would add 1 to both sides. X squared equals 1. Take the square root of each side, and you'd get plus or minus 1. So this function will have a horizontal tangent when the derivative is equal to 0. It will have a vertical tangent, or the function will not exist at plus or minus 1 on the x-axis. Example 6, differentiating quotients with constant numerators. Here we have a numerator is just a constant. Here it's a -7. And then we have a function going on in the denominator. So we have g of t is equal to this. And I'd recommend we could do the quotient rule on it, I guess. And the chain rule would be involved in that. That might get a little messy. Let's rewrite this exponent as a negative. So our numerator is -7. And when we bring this up from the denominator, it changes that exponent to a negative. So we have a 2t minus 3 to the -2 power. Now we can just do a straightforward chain rule. The derivative, g prime of t, is going to equal, bring that exponent down, multiply, you'll get a positive 14, times our quantity unchanged to 1 power lower. Now it's a -3. And then we multiply by the derivative of the inner function. Derivative in here would just be a 2. And to pretty it up a little bit, 2 times that 14 is going to be 28. And since this quantity has a negative exponent, we're going to drop it down to the denominator, and we'll have our 2t minus 3 to the third power. And there we go. That constant numerator wasn't a big problem. Bring up the denominator, change the exponent, and just apply the chain rule.